Hi all. So today we will be dealing the continuation of the characteristic equation and eigen decomposition. So I will be dealing with what is an eigenvector corresponding to a particular eigenvalue of a matrix. So suppose coming to the definition, suppose we are having let A be an n by n matrix, then a non-zero vector v, which is a component either of Rn or of Cn, is called an eigenvector of the given matrix A if there exists a scalar lambda such that Av is equal to lambda v provided v not equal to 0. That is, if this particular scalar lambda is called the eigenvalue of a matrix, we know how to find the eigenvalue of a given matrix, and let us take, suppose let lambda be an eigenvalue of A, then that particular non-zero vector v for which Av equal to lambda v such that v not equal to 0 is called the eigenvector of A. And taking this lambda v to the LHS, we have Av minus lambda v is equal to 0, and taking v common, since v is common, we'll be taking it outside, and we have A minus lambda I into v is equal to 0. Then this particular non-zero vector v is called an eigenvector of the square matrix A corresponding to the eigenvalue lambda if A minus lambda I into v is equal to 0 provided v not equal to 0. So there will be doing problem to find the eigenvector of a given matrix. So this concept will be clear. Let's see this particular question to find the eigenvectors of the matrix A 2 1 1 2, which is a 2 by 2 matrix. So in order to get the eigenvector, first we need to find the eigenvalue. So we know what to do. We'll find determinant of A minus lambda I equal to 0 and get the characteristic equation, then find its roots. So A minus lambda I here is 2 minus lambda 1 1 and 2 minus lambda. Then finding its determinant, it is equal to lambda square minus 4 lambda plus 3, and then equating it to 0, we have the eigenvalues to be lambda equal to 1 and lambda equal to 3. Then using this eigenvalues, we will find the eigenvector. We'll see it. Yeah, we have the value of A minus lambda I is equal to 2 minus lambda 1, and the third entry is 1, 2 minus lambda again. And when lambda, we had two eigenvalues. Let's check, let's try to find the eigenvector in the case when lambda is equal to 1. And when lambda is equal to 1, we'll substitute the value of lambda equal to 1 in the given matrix. So this will be 2 minus 1 1, and here also it will be 2 minus 1 1. So basically A minus lambda I will be the matrix 1 1 1 1. And then to find the eigenvector, what we do is we'll evaluate A minus lambda I into V equal to 0. Since it's a 2 by 2 matrix and V is a component of R2, so let's choose V to be equal to XY. So multiplying the first row and the column, we have X plus Y is equal to 0. We'll compare it with this one, and then the second row into the column will also give X plus Y is equal to 0. So on equating them, this will imply X equal to negative Y. So in fact our V was equal to XY, and now we have the relation X is equal to negative Y. So we will be having negative Y comma Y. And in order to find the eigenvector, just give an arbitrary value to Y. Let's choose, we cannot choose 0, since if we are giving Y is equal to 0, this will be 0 0. Since we need a non-zero eigenvector, let's choose Y to be equal to negative, let it be 1. So Y will be negative 1, negative Y will be equal to negative 1, and Y will be equal to 1. So negative 1 1 is an eigenvector. Okay, you can find infinitely many eigenvalues, eigenvectors corresponding to an eigenvalue. If Y is equal to 2, this will be negative 2 comma 2, and that's fine. You can choose as if of it is of your choice. Okay, you can find the eigenvector by any arbitrary choice. And now when coming to lambda equal to 3, we'll do the same procedure. We'll apply A minus lambda I when lambda equal to 3. So at that time you have the first entry to be negative 1, and here also you have negative 1, and you have the matrix A minus lambda I into V is equal to 0. Since it's a 2 by 2 matrix, let V be equal to XY, and then you multiply, you have negative X plus Y is equal to 0. On both the case you have the relation X equal to Y, and if X is equal to Y, since V is equal to XY, you have the eigenvector equal to, let's substitute it, since X is equal to Y, let it be YY. So you can choose any arbitrary vector, let it be 1. So this will be the arbitrary eigenvector corresponding to the eigenvalue lambda equal to 3. 3. Okay, so this is the way you find eigenvector corresponding to a particular eigenvalue. And for a 2 by 2 matrix, in general case, for an n by n matrix, you will always have n eigenvalues, but you need not have n linearly independent eigenvectors. We'll see such problems. So let's move on to 3 by 3 matrix question. So in this question also we are asked to find the eigenvalues and the eigenvectors of this particular given matrix. So in order to find the eigenvalues, we find the characteristic equation, which is determinant of A minus lambda I equal to 0. So if let's say A what is A minus lambda I, you will be having negative lambda on all the diagonal entries, and determinant of A minus lambda I equal to 0 will give you, since this is since the second and the third entries of the first row are 0, so the determinant will be equal to 2 minus lambda into determinant of this particular matrix. So on simplifying, you have the expression lambda 2 minus lambda into lambda square minus 12 lambda plus 11 is equal to 0. So you know, in order to find all the eigenvalues, you need to factorize this quadratic equation also. So you know how to do that using the formula negative b plus or minus root of b square minus 4ac by 2a. Using that, you have your eigenvalues to be 11 and 1. Okay, so we have three eigenvalues. First one is lambda equal to 2. Here you have, from here you get lambda is equal to 2 is an eigenvalue. Here you have lambda equal to 11 is an eigenvalue. Also lambda equal to 1 is another eigenvalue. So we have the three eigenvalues of this matrix. And now to find the corresponding eigenvectors, we'll evaluate A minus lambda I into V equal to 0. We'll see. So for lambda equal to 2, A minus lambda I is given by A minus 2I, and we have this particular matrix. And let us choose V to be, this is a 3 by 3 matrix. So we'll choose our V to be X, Y, Z. Okay, and then we'll multiply A minus 2I into X, Y, Z. So on multiplying, let me write it here. So this into X, Y, Z equal to 0, 0, 0. So on comparing, first row we have 0 into x plus 0 into y plus 0 into z is equal to 0. We have, that's basically 0 equal to 0. We have nothing, no information about anything. So when we do the second row, we have 0 into x plus y plus 4z is equal to 0. On comparing this, we can find the value of y to be equal to negative 4z. We have a relation here. And then we'll go for the third row, and there you have 4y plus 7z is equal to 0. And from the before case you had y is equal to negative 4z. So let me substitute it here. So that would be 4 into negative 4z plus 7z is equal to 0. This would imply negative 16z plus 7z is equal to 0, which implies negative 9z is equal to 0. This would imply z is equal to 0. So we have the value of z is 0, and if z is equal to 0 and y is equal to negative 4z, we have y also is equal to 0. So now we have the values of z is equal to 0, y is equal to 0. Okay, so basically what was our v? We had the values of y and z to be equal to 0, and our v was equal to x, y, z. So here you have 0, 0, since y and z are 0, then you can choose x to be arbitrary, let it be 1. So this is the arbitrary eigenvector. It can also be 2, 0, 0, 3, 0, 0, negative 1, 0, 0. That depends upon your choice. Okay, now we have the eigenvector corresponding to the eigenvalue lambda equal to 2. Let's see what happens when lambda is equal to the other value is lambda is equal to 11. So when lambda is equal to 11, we find the value of A minus lambda I, and it's given in this matrix form, and we'll choose V to be x, y, z. Similarly, do the problem, and from the first row you have negative 9 x is equal to 0. There you will have x is equal to 0. And in the second problem, you have the relation negative 8y plus 4z is equal to 0. There you have, when comparing and simplifying, you have z is equal to 2y. Okay, and from the from the last row, you have 4y minus 2z is equal to 0. That would imply 4y minus 2 into, instead of z, substitute 2y. There you have 4y minus 4y is equal to 0. There you have no relation, right? 4y minus 4y is equal to 0. You cannot get any relation. So when you are writing v v is basically x y z, and your x is equal to 0, and your y, you have no, let y be y itself, and z is 2y. Okay, so let's choose the value of y to be arbitrary. Let y is equal to 1, so this will be 0 1 and 2 into 1, which is 0 1 2. So this is an eigenvector. Okay, hope you can choose the value to be arbitrary, that's fine, but first find the relation between x, y and z. So this is the eigenvector corresponding to lambda equal to 11, and now corresponding to the value lambda equal to 1, similarly do the process of into x, y, z. So from first relation you have x is equal to 0. From the second one you have 2x plus 4y, sorry, 2y plus 4z is equal to 0, and from there you can get the value of y is equal to negative 2z, and then from the third row you have 4y plus 8z is equal to 0. So from there you have the same relation. You will not be getting any relation more. So when substituting this, x is 0, and let y is negative 2 into z, and let z be z itself. So your relation will be 0. Let's give the value of z to be equal to 1. So it will be 0, negative 2 and 1. Okay, if you are giving z to be negative 1, it can be 0, 2 and negative 1. That depends upon your choice. That's fine. Okay, so this is the way you get the eigenvectors, but in this particular case we had three independent eigenvectors. Corresponding to each eigenvalue we had eigenvectors. So we, from for the matrix A, we had three eigenvectors. Now we'll come to a question. So in this particular question you are asked to find the eigenvalue and the eigenvectors of this particular given matrix, and since you can see, to get the eigenvalue, as we discussed before, find the determinant of a minus lambda I equal to 0, and just see what is a minus lambda I, and just get the determinant. Okay, so you will be getting the determinant equal to lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. Now what we need to do is just factorize them. Okay, for factorizing, what we do is just see the constant term. So here it's negative 4, and see the divisors of negative 4, which are plus or minus 1, plus or minus 2, and also we have plus or minus 4. Okay, now arbitrarily check whether any of them are the roots of this particular equation. Let's try for lambda equal to 1. So when you are having lambda is equal to 1 and substituting in this particular value, you will be having 1 minus 6 plus 9 negative 4, which is equal to 0, which means lambda equal to 1 is a root of this particular equation. This will imply lambda minus 1 will be a factor of the given cubic polynomial. Then use the synthetic division as I mentioned before. Do the lambda minus 1, since it's 1, write it here 1, and just take this 1 to the bottom, and then multiply 1 into 1 and write it here. Then add negative 6 plus 1, which is negative 5. Then multiply 1 into negative 5, which is here negative 5. Then add 9 minus 4, which is 4. Then multiply 1 into 4, and you have 4, which will be, last entry should be 0. Then write this to be the coefficients of the second degree polynomial, which is 1 into lambda square minus 5 lambda plus 4 is equal to 0. So you have the second degree polynomial now. Then by splitting the middle term method, you can see this is lambda minus 1 into lambda minus 4. So basically this particular cubic equation, since lambda equal to 1 was a 0 before, this will be lambda minus 1, and again lambda minus 1 into lambda minus 4. So you have the roots to be equal to lambda equal to 1, 1 and 4. Okay, here is the problem. We'll see whether we can get the two linearly independent eigenvectors in the case when lambda is equal to 1. We'll see that. In case lambda equal to 4, we have find the value of a minus 4i, and we have this particular matrix. Let's choose xyz to be v to be xyz, and then just multiply the first row. You have minus 2x plus y plus z is equal to 0, and then doing the second row you have another relation, and doing the third one you have another relation. Okay, now what we do is we'll just add the first three equation, and then you can see that's equal to 0. Okay, when you add all the first three equation, you can see 0 is equal to 0. You will be getting no relation. Now what we do is we'll subtract this second equation. So this first equation from the second equation, equation 2 minus equation 1, and then you can see you will get the relation 3x minus 3y equal to 0, which implies y is equal to x. You can take this 3y to here and can cancel 3 to get x is equal to y. So you have a relation now, and now what you do is you will just substitute this in the equation 3. So what happens is x plus x minus 2z will be equal to 0. This would imply 2x minus 2z is equal to 0, which implies z equal to x. So we have y is equal to x and z is also equal to x. So which means v is equal to x, y, z is same as x. Y was equal to x, so this is x, and z is also equal to x, so this is x. So to find the eigenvector, just substitute the value of x is equal to 1. Okay, then you have the eigenvector. Now we have the case when lambda equal to 1, and when lambda is equal to 1, what happens here? Find the value of a minus 1 into I. You have the matrix. Then what you do is take the value of v to be x, y, z, and when multiplying them and equating that to 0 0 0, we have x plus y plus z is equal to 0 from all the three equations. Is it? So what you can do is, the only thing you can do is x is equal to negative y minus negative z. Is it? So what we do here is our v was equal to x, y, z, and you have the relation x is equal to negative y minus negative z. So instead of x we will be writing negative y minus negative z, then you have y, then you have z. Okay, now what you do is just give arbitrary values to z and y also. Okay, so first eigenvector would be, let's give z to be equal to 0, z is equal to 0 and y is equal to 1. So what happens is z is 0, y is 1, and what is negative y minus negative z? That is negative 1 minus 0, so that would be negative 1. So this is a particular eigenvector. And now if I'm giving whether I can construct a vector linearly independent from this vector, that's what is the case in finding eigenvector. So let me give the case when y is equal to 0. Okay, when y is equal to 0, and let me give z is equal to 1. So 0 and 1, this particular vector is not a multiple of this vector, so they can be linearly independent since y is equal to 0 and z equal to 1. And now what happens here? Y is 0 and here z is negative 1. So this both are the eigenvectors. You can choose it in a different way also. Okay, you can choose the value of y to be equal to 1 and z to be equal to 1. At that time it would be negative 1 minus negative 1, which is negative 2. Negative 2 1 1 is an eigenvector. That depends upon you. You are completely free to choose the arbitrary values. Since we had the repeated root, we can get, we had lambda equal to, that was 3 I guess, and lambda equal to 1 as the new eigenvalue, and this was a repeated root. So sometimes we will be getting two eigenvectors here. Since we had two arbitrary variables, we will be getting two eigenvectors. There are cases when we will not be getting two eigenvectors. Okay, even when the roots are repeated, we'll discuss that case now. So in this particular case, when lambda is repeated, lambda equal to 1 is repeated, and in the same, for the same eigenvalue, we'll be getting two different eigenvalues. Okay.